We are back here on Deutsch algorithm. Okay. So, okay, try to remember this picture. Try to remember this picture and we will see that how we will work, how we'll create this unitary function with the help of any program. Okay. Actually, Deutsch algorithm, because this was some hypothetical problem. So the program of this algorithm, there is no direct program of this algorithm. We had to come up with some kind of technique to convert that unitary into some circuit form. Okay, and we have just seen a glimpse of that circuit in Grover's algorithm. We have seen that we were applying CNOT gates in order to do the phase kickback. Okay, and you remember this particular equations that we talked about, -1 power f of x and then y state, if you remember it. So this we came up with while doing the unitary function, this unitary function, y or f of x. So let's see how to solve it first of all. In order to solve it, so we consider that a function can be constant or a balanced phase. Okay, so in that case, four things are there, four type of constant inputs and outputs we can create out of it. So first of all, if we start with the 2-qubit case, and suppose this is your input, and we want to check that for this particular input, what is your if your function is a constant or a balanced, and this is your ancilla qubit, which is y over here. Okay, so to check that particular thing over here, whatever f of x is doing, y or f of x, it is that unitary function is doing y or f of x. So our main thing is only to convert that y or f of x into the form of program. Now for the constant function, if you remember, everything, the x case, the x value would be 0 if that function is a constant, and 1 if that function is a balanced. So in some way, if you understand it, for the constant case, we are not doing anything. The function is not reacting. Function is just giving us the same output, whatever input that it is getting. Okay, the same thing it is producing. But for the balanced case, it is changing a little bit. For 0, 1, 1, 0, or somewhat around that. So our main focus is to use that balanced function. The functionality of that balanced function we have to convert into form of program or into the form of circuit. Okay, so for that there was one thing. First of all, if you have 0, 0, you are starting with a Hadamard gate. You apply Hadamard gate, you will get a equal superposition state, and this will be if you apply Hadamard on this one, that would be 0 minus 1 by root 2. This is the same thing. This is the Hadamard, just application of Hadamard that we are getting. Okay, here we do not have to think about anything. The main part is unitary. For the unitary case, as we already have seen in Grover's algorithm, which Grover took from Deutsch algorithm, that we apply CX gate, continuous of CX gate. Okay, so x, this is our x, there are 2 qubits. So what we do, we apply Cx from 0 to 2 and 1 to 2. So this is what it is saying. Cx gate, control NOT gate, 0 would be your control and 2 would be your target. 1 is control and second is target. So if you apply that particular thing, so if you apply that particular thing, you will end up getting this state. This is a very big state, you have to solve it. Okay, so what will happen? What it is representing? So it is representing that if you are getting a Cx, if you are doing Cx 0 to 2 and 1 to 2, that is the same thing if you do a XOR operation between these two and this one. Okay, so this is just a expanded representation what we have done. Just 0 0 would be constant, 0 0 can be taken out because that is x, our x over here, and this later on for the y case we are doing a XOR operation between both of these and one this, and again both of these and one this. Of course we have just expanded everything. So what is happening over here? Okay, so here we are taking 2 qubits. We are starting with 2 qubit over here. This is 1. Hadamard we have applied equal superposition of all those basis states, and this will become minus. Now for this case what we are doing, if we are considering 2 qubit, we are applying C0 gates from 0 to second, 0 to second, first to second, because 0 and 1 are our input. Okay, so that is, if Cx we are applying 2 times, so that is equal to doing a XOR operation. Okay, so that is equivalent to doing this mathematically. Okay, if you do that particular thing and resolve it, it's a very easy mathematical calculation that we will get at the end, because we know 0 XOR 0 XOR 0, that would be 0, 1 XOR 0 1, and 1 XOR 0, that would be 1 again. So in the same thing we have to apply the same function over there, and we will see at the end, after doing all those computation and taking the common out of it on all those things, at the end what we are getting, this is, if we apply, this is at the end we are getting, if we will apply Hadamard gate on this, both of these are x, because we will get 1 1. So that means our function is balanced. So only by applying Cx gate we can convert that unitary function that we can write in the form of circuit. Okay, for the balanced case. And for the constant case, because we do not require any phase kickback on in the constant function, we do not do anything. Okay, so this we will proceed from here. So this is what our oracle would look like. Okay, this is what our oracle would look like if we are considering 3 qubits and 1 is y. This is your x and this is y. Okay, 3 qubits we are considering as an input. So we have to apply 3 C0s. Okay, that is 3 inputs. Y is ancilla. This one is ancilla. So yesterday, or in the when I explained about the Deutsch algorithm, that time also I have explained that those zeros are our input. This is just helping us, okay, in order to check that a function is constant or balanced. So this is what we have got till now. Okay, so this is what our unitary function would look like in a form of a circuit for the balanced case. Okay. Now for this, there are little change that we have done over here, or you can go other way around as well. We know that if we are having input state in all zeros, our output would be 0. For the simple XOR operation that we would know. For this case, we would be getting output as a 1. All those things, just a little computation that we did earlier. The same thing that I have shown over here. So in the constant case, okay. So in the constant case, how the oracle would look like, there would not be any oracle in that case, because we will apply Hadamard gate and will do the measurement, whatever result we will always, because this is a simple calculation. Hadamard and Hadamard would be if we do matrix multiplication of Hadamard and Hadamard, that would be identity. Okay, because these are reversible in nature. Quantum circuits are reversible, gates are reversible in nature. If we reapply the same gate on we will get identity. So this is what we will get for the constant case. But for the balanced case, this is the same computation till here, and for the unitary function we will apply a C0 gate, and then we will apply a Hadamard, measure it, just that. So this, because here this phase kickback it is doing, so this will be converted into 1. So this would be our balanced case. So this is the thing. So we can easily do the circuit over here. We do not have to bother about any vast programming thing over here. So what I am doing here is I am just creating any random integer, means any value that I want to check if that particular value is a constant, if that particular value, if I provide to a function, if that is giving me constant or a balanced case. So I just have to do that. So I'll apply, what I'll apply is I'll apply X gate, because I want to put this main thing is I have to do is this set of Hadamard and X gate I have to do. Just the same thing, basic thing in constant in the oracle. So this is what your circuit would look like in the case of constant, if your function is a constant. Okay. So the results here, I'll describe you the program later on. So result here is 0. Every qubit is 0. That means your function is a constant. And for the balanced oracle, this is what your circuit would look like. I have not applied Hadamard gates in the initial and Hadamard gate in the end. Just these C0 gates you have to apply. Okay, so this is the entire circuit, your entire circuit, your oracle, the entire oracle would look like. The in between C nodes are your oracle. And the measurement, because I have done both of these functions separately to check that my balanced or a constant function is working properly or not. So for the balanced case, I am getting all 1. So of course I check that my constant and balanced function are working properly. So I just combine both of those things. Okay. So in here, this is what I have combined everything. So in here, in the oracle, this oracle will be activated when my function would be balanced. In that case, it will apply C0 gates. And if my function is a constant, in that case, it will apply, it will do nothing. Okay. So just as it is, the thing will go. Okay. Okay, so let's see. So for this case, what I have to do is, I have to provide, because this everything is, the circuit for both of those constant and a balanced case is different. Okay, so circuit is different. For that case, either I have to add some if operation over there, or I have to check, if I have to tell the program that if I'm checking for the constant function or a balanced function. Okay, so that's why I told you that this is this Deutsch algorithm is not like a program based on input it will decide the function is a constant or balanced. I have to check because this was a hypothetical problem. Both of the things were not related in a way so that we can create a program out of it. So that's why I have to check if the function I'm looking for is a constant, or I have to check if my function is I'm looking for is a balanced. If I'll say that I'm looking for a constant function for this particular set of inputs. So for that it will see this and give me some output. And for the balanced case, it will just apply that oracle and give me some output. So based on the output, I have to decide whether my function was constant or a balanced. Okay, a little tricky, and there is a little task for you to do is check if we can create a DOS proper program. I have given just 2 different functions over here, and I'll ask you, this is actually a task over here, that try to check if those functions can be combined together in some way so that it can be created a proper program. Okay, I explained the functionality of the unitary, means whatever oracle that is, how it can be used, how it can be converted into some kind of circuit. So now it's your task to see that if you can create a program out of it. Okay, proper program out of it. That's why I have written if the case is balanced or if the case is constant. Okay, because both of those things are not related. We cannot create one single circuit that can check for the constant function or balanced function. Either you have to add some noise into it to see what is happening, or some other way you have to come up with. Is there any question in this? Okay, I know I've given you a task. Okay, but let's see, if you are confused in the oracle, the designing of oracle, are you confused? Is there any question in designing the oracle? I think no one is. Okay. Now, if everyone was interested in seeing some quantum machine learning algorithms, okay, I think this would interest you, all of you. So here I'm working with a quantum support vector machine, quantum kernels. Okay, generally what we call a quantum kernel. So this is the main support vector machine. This is what I talked about in the last session, that how a support vector machine works. Just find out a hyperplane that can classify both of these kind of data points. Okay, and these equations corresponds to the hyperplane. This corresponds to the hyperplane, and this corresponds to the point, if it is negative points you can say, or these are the positive points. Positive classification or negative binary for the binary classification we have to see, and the hyperplane should be as far as possible from these points. Okay, so this was what SVM, generally a classical SVM looked like. And of course this also we have seen that if we have a non-linear data set, in a single line I have represented a non-linear data set actually, and if we have to classify that non-linear data set, we have to go to higher dimension case so that we can linearly classify that thing. Now this is the main equation we are interested in. This is the main equation we are interested in. Here y is the label, alpha is some Lagrangian parameter, and k of xi xj. So this k of xi xj in linear case, this is just an inner product. Okay, and for the non-linear cases, this k of xi xj could be any kind of function. That could be a RBF kernel, radial basis function kernel, or many other Gaussian kernel or other kernels are there. Okay, and B is some biasness that we can introduce into the program. Okay, so we know SVM. How do we do SVM? How do we use that SVM? We have taken so there is a sklearn library from where we can import that SVM, and we do not have to do anything. Just using that library, we can provide some input data points, and the output data points we just have to provide it, and it will give us the results. I'll show you. So in this case, I have taken some data set from Kaggle. This is a very basic Titanic data set I have taken. Okay, so here I have just taken that data set, and xtrain over here represents a data set which represent for the training case, training features, and ytrain represents a training data set, labels of training data set, and xtest test features, and ytest y features. Everyone, I think most of you are familiar with this thing. Now for the simple basic classification, I told you sklearn you can use. Sklearn, from sklearn you can, I am not going into detail of this SVC. So in SVC we provide just training function for the training purpose, and then for the testing purposes we predict this model. And of course, for after predicting, you would be requiring, you want to classify and you want to check how that model is behaving. So for that case, we will check 4 basic parameters, evaluation matrices, 4 basic evaluation matrices: accuracy, precision, recall, F1 score. Okay, so this is your accuracy. For this model is predicting 79% and giving us the 79% accuracy, and this is giving us the precision result, recall, and F1 score. So you precision and recall and F1 score. F1 score is just a average of these, geometric average of these precision and recall. And precision is precision provides you. If I'm confused, just let me know, because I generally get confused between precision and recall. Just gives you the parameter which are accurately, positive parameter which are accurately classified, and this for the negative parameter which are accurately classified. If I'm wrong, please correct me. Okay. So this is what your result would look like. So let's go to quantum support vector machine. So as I mentioned, okay, here it is not showing us. Okay, so first of all we have to do the feature mapping. Okay, as someone was asking me, is there any kind of library or something? So there are 3 kind of libraries. From Qiskit you can directly access those. The feature map, those are the feature map libraries actually. Z feature map, ZZ feature map, and Pauli feature map. Okay, you can go and look for it. So these feature maps ask you for the feature, what is the dimension you want to have, or what is the dimension you have in your data set, and how do you want to use this particular circuit. Means if you want to use a single repetition of it, or if you want to do a double repetition of it. Why you want to do these kind of repetition? The similar way as you do in SVM, there are hyperparameters, right? So you tune those hyperparameters. So these are the hyperparameters that you tune. Okay, entanglement full, or there are 3 kind of entanglement generally that we use: linear, full, and circular. So linear, by linear you mean this and this, these are entangled, and these and both of these are entangled. Okay, entanglement, because Hadamard and CNOT kind of entangle these states. So initially we will always use Hadamard gate to make use of that high dimension space. Okay, so that's why Hadamard that we do, and this is the linear entanglement. For the full entanglement, everything is entangled with every other qubit. Okay, and for the circular case, we just apply another circuit over there, another CNOT over there. Okay. So, and there is one more thing I want to mention. Any unitary function, if it is based on theta, we always write it in the form of exponential of theta thing. Okay. Generally for the rotation matrices we do that. Okay. So this theta, as I mentioned earlier as well, this theta can be theta by 2, pi by 2, 2 pi, or any of these kind of representations as well. Okay. So this is pi minus x1, pi minus x3. There is some kind of relationship over here that what is happening over there is this is the thing. Most of this is also known as ZZ feature map. Most of the time what is happening is in ZZ feature map gives us the best result in classification. So what it does, it does this superposition, creates a linear superposition of states and then creates an entanglement. Okay. After creating an entanglement, it takes into account both of the theta parameter corresponding to feature F1 or feature F2. Okay. So that's how this is your feature F1, this is your feature F2. This is how it represents. And it creates using those parameters, it creates a theta parameter which would be your classical value, any classical value, anything, pi something, and then again C naught. So actually it has been mentioned that somewhere in the research articles as well, that this particular circuit kind of distribute your data points on all over the Hilbert space. So it was in a research, it was mentioned that the more your data set would be distributed on the Hilbert space, the more the classical machine learning, the quantum machine learning algorithm would be able to classify. Okay, so I have given here all equations for the Pauli feature map and ZZ feature map, all those feature maps, and how do you customize your feature map as well? Means instead of pi minus xi, you can use sine of pi minus xi, or there are different functions over there, data mapping functions. These are known as a data mapping function. So these data mapping functions you can change according to you. Okay. Now this is your kernel k of xi xj. Classically you write it in form of this. Now this function, in the previous session we saw that this can be written as an inner product, and that inner product, if you're considering the feature map and all those your unitary functions into the case, this can be written in this form. Okay. And of course this is a normalized square, that means at the end it is representing your probability. Okay. So instead of that k of xi xj, we can just directly put that whatever value that we would be getting from this inner product, we would put that particular value in here and use the classical support vector machine to do the classification. So in here I am considering into account this ZZ feature map. The same data set that I have considered earlier, the Titanic data set, I used the same data set over here. So in that Titanic data set I was having 7 features and I'm just using it for the 1 repetition. 1 repetition means this is my 1 repetition, and if I repeat this circuit again, that would be my 2nd repetition. and entanglement full case I'm using. And this is known as fidelity. Okay, fidelity is the one that tell you that how closer your data points are or how far apart those your data points are. So that's why there is a fidelity. Based on this, there is a fidelity state vector kernel to compute that fidelity function over here. And after computing, because your quantum kernel, you will get some quantum kernel at the end. You will get some quantum state, and that quantum state you have to provide into QSVC. QSVC does nothing actually. It just compute that kernel values and put it. It has some behind SVC, classical SVC function. It just uses that classical SVC function with only your kernel function value. Okay. And then of course, as similar way in SVM as we do in SVM, just fit our training function, training data point, and then predict. So result is in front of you. Earlier we were getting 79% accuracy, and we using this ZZ feature map and computing a kernel value, you are getting 81% accuracy. So if you are using, this was the simplest case just to show you how to import your libraries, how to use those libraries, and what kind of parameters you have in all those functions. Okay, so you can use this directly. And there is one thing I mentioned, I didn't mention over here. There was a sampler in here. So this is the sampler is the new function in Qiskit used to do your simulation. Okay, so this comes under primitives. So there are two kind of samplers: sampler primitives and estimator primitives. Sampler primitives is the one which gives you the probabilities. Okay, probability corresponding to 0, 1, 0, 0, 0, 1, whatever combinations, basis states you have in your data set, that kind of probabilities. An estimator QNN would give you the eigenvalues. Okay, if you are working with any chemistry kind of problem, variation quantum eigensolvers you are working with, if you are working with that, so you would be interested in eigenvalues, minimum eigenvalues you would be interested in. So in that case you have to use these estimators. So in here I have also given, you can also see at the end I have given an example that how you can use IBM quantum systems, how to access those IBM quantum systems into your programs. Composers are easier to access those IBM quantum system. In this case you have to use this Qiskit runtime services. This is a library, you can say, IBM quantum runtime services, Qiskit runtime services. From there you have to provide your channel, that is IBM quantum only most of the time, and for token you have to provide API token. Once you create your user on this IBM composers, you will get a API token from there. So that API token you have to store here. And yeah, these are some functions that I have used. Whichever is the least busy one, I want to use those particular IBM system only. And I just shown you how to give a job to it and how to get the output. Same thing for the estimators I have done. Okay. Okay, so any questions in this quantum kernels? Of course, once you implement it yourself, then only you would be able to understand that what kind of functions you can use and what kind of functionalities and all those things. Just given an example over here. I think I can stop here then if you don't have any questions, or you can talk to me later on. Okay. Yeah, everything is in Jupyter Notebook. Okay. I'll give this notebook to you, and sir can provide to everyone, or on the LMS portal you can check for the code. You just, okay, I'll provide you the data set as well. And if anyone interested in these quantum kernels, I've also shared a reference here. So this you can go and look. Okay, so this was the first, this person Havlik provided these feature maps, different kind of feature maps, and he proposed this quantum kernel algorithm actually. This particular kind of quantum kernel algorithm. Okay.
Classical data to be converted to quantum.
We have used feature map. Those feature maps are ZZ feature map. The name it specifies feature map.
Is there any constraint over the type of the classical feature type?
No. Okay. First of all, if you have a numerical data set, you can directly use these feature maps. If you have a text data set, in that case, first you have to convert your text data set into numerical form. That we do in classical machine learning as well. Okay. Because every machine learning algorithm at the end, it is a computer generate. It will at the end, it will go into the computer or your system that only understands in the form of 0 or 1. Okay. So you have to convert, you have to do your part. You have to convert that into numerical form so that it can be converted later on into 0, 1 binary form, whatever it requires. Okay, so yes, text data at the end, only the numerical points. And at the end, there is also a question, what kind of feature map do you use? What kind of circuit do you use? So you have to go hit and try and check what is working for you. The one thing is that. Other thing is go into fundamentals. Okay, what kind of at the end you have to check, like earlier I have shown you the kernel efficiency. You have to check how the kernel is behaving. Because at the end this is also giving you some kernel values, and classical is also giving you some kernel values, and everything is dependent on those kernel values. If those kernel values are linearly classified, that means your program is working fine. If it is not doing linear classification, that means you have to use another kernel. Okay, let me stop here.
Start. Start. Okay, hi everyone. Very good evening again. So this is Devendra, and as yesterday we discussed quantum entanglement and quantum storage of quantum information. Today we will be discussing something application of those technologies, which is called distributed quantum computing. So we had discussed how entanglement can be generated and what are the experimental procedure of it, and all of my colleagues already discussed a lot about the computing. So today we will discuss something which connects quantum communication and quantum computing both together. So earlier quantum computing was separate, quantum communication was separate, but now both will be amalgamated together, and then this topic will be emerged. So first we will discuss what is it and why it is required. So distributed quantum computing is something, so let's say you have a one quantum computer which has certain qubit, let's say 10 qubit quantum computer you have. It cannot do certain operations, and another person has another quantum computer which has again 10 qubits, and so on and so forth. So if those processors, both quantum processors can connect together and working, either directly connected or virtually connected. So virtually connected means entanglement between those processors. So they can do a very strong communication in between, and then computational power will be at the same time increased. So this is called distributed quantum computing. So a single processor cannot do the job, and combined multiple processor, either local or non-local, they can conduct a very enormous computation. So that's called distributed quantum computing. And so the distinction is, here we use entanglement. So entanglement is something called non-local phenomena. So without directly connecting the two particles or parties, quantum information can be shared by teleportation. So we are going to utilize that power of quantum technology and connect two remote processors that can do computation simultaneously. So that is something called distributed quantum computing. So today we'll be discussing fundamental principles and components and architectures, entanglement role, why it is very important, and challenges in the future. So in the distributed quantum computing, you see there are multiple processes. First, you are going to generate entanglement. You can connect two systems simultaneously and then started computing. So we'll going to discuss that. So before deep diving into the system, I will quickly discuss the status. So you can see what is the present status of quantum computing. So IBM Quantum has 433 qubits by 2022, and their roadmap by 2025, they are projected to go around 4158 qubit quantum computer. So that's the present status, state of the art, present worldwide status. Other major players like Google, Amazon, Microsoft actively working on that, but IBM's progress is the best so far. EU flagship, they in European Union as well, they are using, they are making a lot of progress, and China has already heavily invested in quantum computing, 25 billion. And but we have to check the reality whether present time quantum computers can do a practical problem solution or not. So practical solution, for example, optimization algorithms and whatever we were discussing, right, or breaking some sort of encryptions that are already established. In previous sessions you might have heard that by using quantum computer you can break the very strong encryption, right? So but what is the number of qubits which is realistically required to break the present infrastructure or present encryption system, that we need to check. So presently qubits are not very, like they are not very precise. It's called NISQ era. So they are not very fault tolerant, and they are noisy. So, and the number of qubits are also yeah, sorry, can you just make it full scale? Okay. So number of qubits are also not very much high. Like I will show you the exact number of qubits which are required to do some realistic operations. Noise is there, scaling challenges like multiple type of qubit, ion traps, superconducting circuits or quantum dots. They all encounter scaling problem. They cannot go very high number of qubits. So, so as already we have seen, 1981 Feynman proposed qubits, and 1994 Peter Shor proposed first algorithm, Shor's algorithm. 2016 IBM launched first cloud quantum computer, and 2022 433 qubit, and projected is, just remember this number, 4158, which is the highest presently in 2025. So we can see exponential growth in the number of qubits, and the whole world is investing heavily in this technology. But what are the realistic number is required? So you see, I am sorry because these fonts are very small, you cannot read it, but this is machine learning. It's written machine learning. This is something called cryptographic application and quantum chemistry. So number of qubits are more than 8,000 or 12,000, something like that. That's the number. So presently we are at 4,000 and requirement is 8,000 or 12,000 or more. So we are not arrived yet. So question is by when we will be arriving, or what are the solutions? If we are in the same phase, what are the other solutions? That is the question. So required qubits are more, thousands of noise free qubits are required, and extremely low error rate are required, but hundreds of noisy qubits are there presently and higher error rate. So to conduct a present system, by using present system, how we can do a very high level of computing, then distributed computing can give the solution. So if we can connect a multiple processor which has, let's say, 1,000 processors, and we connect them with the entanglement and teleportation, they can do the enormous job. So presently the NISQ there is I also have given the comparison between different superconducting trapped ion and photonic qubits, neutral atom. So this is just additional information where you can see what are the different devices and what are their parameters, like what is the room, is there the temperature they are working, either room temperature or low temperature, what is the fidelity and what is the scalability, like an example of such type of qubits. So this is just a NISQ comparison of all the qubits. And again, definition of the NISQ, like noisy intermediate scale quantum. So qubits will be limited in number, there will be noise, and the coherence time of qubit, because we don't have very strong storage time of quantum memory, so coherence time of our qubits are also very less, and error correction is not very so theory has been established, but in practical error correction is yet to be fully established because of the number of qubits. So this is the NISQ that we are facing present time. So this is the limitations. So just look at this picture very carefully. So these are the number of qubits. So from 2, 4, 6, 8, 10 number of qubits. So if and this cube is showing us the how much power of computation can be done. So here small cubes are given, and this axis is number of qubits single device, means single processor if working, or 2 isolated systems, 4 isolated systems devices, and 2 distributed devices. So you can see if number of qubits are increasing and you are doing a distributed system, the computation power is increasing enormously. So that's the power of distributed quantum computing, and you can get a very high power if you will connect multiple processors by using your entanglement or teleportation. So that's the one pictorial representation of how the power of distributed system will going to be increased. Again, the same similar kind of data. So it will be increasing exponentially as well with the number of qubits, and if processors will work distributed function. Again, let's quickly see the fundamentals. So I will not going much into it because already we have discussed a lot, like superposition, entanglement, measurement, Snow cloning theorem. So I will not going to be deep into it. And what is the difference between the classical versus quantum distribution? So classical as well, distributed processors are working presently. So we can connect multiple processor either at same place or different place, and they can work in a distributed function. So just like in your laptop, you can add different processor or RAM, and you can connect together and they can work and your performance is better. So this is something called classical distribution, classical distributed computing. But quantum won't work like that. Because of the no cloning theorem, you cannot directly connect two processors, and so you have to establish entanglement between them. So multiple quantum processors, you have to establish entanglement, and accordingly they will work in a distributed manner. So the difference is, classically if you are distributing the processors, the scale will be very linear, as very obvious, and but data copying and broadcasting will be very easy, and it's a well established protocol and framework, so you can use it. And bandwidth limited communication, that's also true. But in quantum distributed computing, there will be exponential scaling. So here is n times performance increase, but here 2 to the power n times performance will be increased. So again, this is one exponential speed up in the scaling. And no cloning theorem prevents copying, as we discussed, and entanglement as communication resource. So here directly, as we discussed, we cannot connect. So entanglement is required, and fundamentally different paradigm totally from the classical computation. So now we'll start discussing the DQC, distributed quantum computing. So we will discuss on so it can be categorized in 4 type of vertical. So on the basis of quantum algorithm, on the basis of quantum networking, and quantum compiling, and the simulation tool. On these verticals, we can discuss on a 4 ways in distributed quantum computing. Okay. But I will mostly focus on quantum algorithm and quantum networking, and I will give the reference of these 2, and you can check by yourself. So it will be introductory. So so what are the main problem? So you have, just like Diksha, she was explaining a circuit, right? The circuit is big, and if you want to use a distributed quantum computing, you have to break the circuit into, let's say you want to separate into 2. So you have to break the circuit into 2. So, but quantum circuits are not that easily breakable. So they are called monolithic operation. So in a single processor, you have to conduct, so this is a quantum processor, and there are multiple qubits, they are connected with each other. So mostly examples like quantum Fourier transform, or Schwarz algorithm, or Grover search, or Diels-Josha. So these algorithms are monolithic in nature, and they are being designed to operated on a single quantum processor. So first you have to do some manipulation, you have to break your quantum circuit into how many distribution you want to do, how many processors you want to break, that many pieces you have to break your initial quantum circuit, and then you have to check whether a distribution can be done or not. So this is the major problem will be arising once you are started distributed quantum computing. So few algorithms are inherently you can break them into pieces, but few of them are not possible. You cannot make it in a pieces. So these will be the core problem. So we have to do some. So now you see, this is one operation where you have at one Hadamard, and then these one C naught, and again one more C naught and one C naught. So here one processor and another processor. So you have to do some technique. Let's say you broke a circuit, and then you have to apply a technique where you can connect them with. So this gate is non-local. You see, this C naught is local, this Hadamard is local, and this C naught is local, but this C naught is non-local. So we have to do certain non-local operations, which I will be coming into next slides. but you understand the core problem. So we have to find out which type of quantum algorithm can be effectively, partitioned, how you can do partition, and how can a linear processor communicate with each other by using entanglement or teleportation, and what will be the theoretical and practical overhead in terms of time, additional qubit, and require entanglement resources. So problem is very clear. You have to make a partition in your quantum circuit, original big quantum circuit, and you have to do some non-local operations. So these are the two main problems. So this is one example. This is a circuit of quantum Fourier transform, and this is a monolithic design, and you have a n qubit, and these are the operations Hadamard and then rotation R1 R2, and similarly they have a huge circuit and there are multiple operations. This is a quantum Fourier transform. So this is a monolithic design, but if you want to do in distributed function, you have to break it, you have to use your multiple algorithms like variational algorithm or different other algorithms. You have to make a graph out of it which have a node and mesh and multiple other things, where you will translate the whole this kind of circuit diagram into a graph problem, and then you can distribute into multiple smaller graphs, vertices, and then with different processors you can choose and you can distribute. So but this process is not very straightforward. So that one example I have discussed. So what are the approaches to do the partition in a quantum circuit? So one is graph based partition, as I discussed. So you have to do some kind of hypergraph, as Diksha was discussing in the machine learning. You can see these techniques where you can make a hypergraph representation where there will be cuts and nodes where circuit and different qubits can be represented by the vertex and the edges of a particular graph. So that is one approach to do the partition inside a circuit. Another is application specific, like variational quantum eigensolver or quantum phase estimation or distance based classification. So this is the another technique where you can use them to do the partition between your quantum circuit. Other one is a dynamic. So either you can do a partition in one shot and you distribute your circuit in different processor, or you can do dynamic partition as well. So you can so one part is separated and executing, and real time you are separating and executing. So that's called dynamic partition. So that is also classified in it. So at the end I am giving a reference where the whole detail is given. There's a survey paper you can go through and you can find the algorithm and very much detail of these. So these are the strategies of partition between the quantum circuits. Next challenge. So till now what we discussed, what is distributed quantum computing and why this is important, and what are the main challenge like partition and all, and how entanglement can be existed between the multiple processors, and what are the strategies to do the partition in the quantum circuits. So now let's say we are able to tackle the first problem. We made the partition, we have a whole partition of we have multiple processors we have at your end, and we have all the circuits as well. Then what will be the challenge? How you will distribute the problem between the resources, how you will allocate. Let's say all processors must have a same number of qubits, or else they have different number of qubits, and you have to distribute, and they might be a different distance. So it will be some kind of a quantum network type problem where you establish entanglement between multiple processor and you see the power of processor as a resource, and then you create a network out of it and manage between that network how you will distribute the problem or your circuit partition. So this is called execution management, and you can orchestrate distributed quantum computation. So multi-user scenario, resource allocation, timing and synchronization. So you have to have a central controller that should have all the information of different processor between the quantum channel and classical channel in between, and you can establish a network that would be a global information that is with a central controller, and all the routing strategies and resource allocation strategies, that should be a rules based kind of system that should have with a central controller. And then multiple quantum processing units, it will dictate accordingly how resource will be allocated and what will be the computational power. Based on that, this resource allocation will be happening. So this is whole the management kind of system, and we have the like routers these days, right? The network routers. So that kind of thing can be done with the orchestrating distributed quantum computing. What will be the metrics for this? So what is the throughput, quantum volume throughput, fidelity, preservation, and communication ratio. So these are the main basically points that based on that you will do the execution management between a central controller of quantum distributed computation. So this is the other one. So now we'll discuss the network. So quantum network will be going to play a very significant role in distributed quantum computing. So there is difference between classical network and quantum network. I already discussed in previous session few of them. Now we'll again discuss in little bit detail. So information cannot be freely copied. Like information, here no cloning theorem and prevents copying of unknown states, but in classical there is no problem, you can copy. Reading data doesn't change it, but in quantum if you read it, data will be destroyed, so you cannot read in between. And decoherence time is not the case like in your processor. In classical, whatever you will store, it will be for a trillion years, it's not going to die. But quantum, there is not the case. There is a limited coherence time and data destroys after a certain amount of time. So this is another problem. And here classical, there is buffering, and there is no, you have to connect it with a direct connection. But in quantum there is an entanglement which act as a spooky action of the distance, and it can connect without directly connection, your data can be transported or teleported. So this is one example of a, so you see there are 3 processors, and you can see every processor had 2 types of qubits. So you see white qubits are like computing qubits, and that colored one is a communication qubit. So every processor have 2 types of qubit, one which only involves in computing and the other which involves in communication between interprocessor, basically interprocessor communication. So this colored one is an interprocessor communication. So which qubits or processors are directly connected, it's called a quantum line or quantum link. So you see here and here it's directly connected, and this one is directly connected, which is quantum link. But you can do something called entanglement swapping. In last discussion we had discussed where you can swap the entanglement by using Bell state measurement. So you can also connect to, without any direct optical fiber or something, you can connect to processors, which is called virtual quantum link. So what we discussed, multiple quantum processor, types of qubits involved, computing, communication. Direct link is quantum link, indirect link is virtual link. So that's how whole network will work, interprocessor communication. And one thing is not shown, classical communication is constantly happening between all the processor, which is kind of understood, so it's not shown. But please do not get confused that without any classical line, I have stressed in last teleportation discussion as well, a classical channel or classical communication is constantly happening and nothing is going beyond the speed of light. So a classical channel will be connected between the interprocessor, that is understood. So now I will give one example of quantum communication network. So there is a protocol called BB84 protocol, where between two parties how you will communicate. So yesterday after the entanglement discussion I did not discuss any application, but today we will discuss that. So far any questions, any doubts? Any questions or any doubts you can ask? Previous slides. Yeah.
Here, the dotted line is a quantum computer.
Yes, these are the quantum processor. Yes, quantum computer. So there are. So let's say this is a 4-qubit quantum computer. 5-qubit quantum computer. Yeah, where 4 of them are data qubit or a computing qubits, and this one is communication qubit. Okay. Any other questions? So it's different qubit which has some kind of transducer. So transducer is which converts a different type of energy into different form. So for example, thermocouple, correct. So similarly, so just think in our quantum computer, this can be a superconducting. And here this communication is optical communication. So this qubit which is in touch with optical qubit plus superconducting qubit, they should have a transducer which can convert that information from superconducting qubit to optical qubit. So very good question, sir. So this is I'll discuss separately. Very significant thing is that, and lots of experiment is already going on in the transduction of different two types of qubit don't talk to each other. Superconducting will not talk to ion trap, or ion trap will not talk to photonics, and photonics will not talk to photons traveling in outside. So distributed quantum computing will be very difficult if this transduction will not be happening. So transduction can be done multiple ways. I have not given a very much detail, but we can discuss separately this transduction technique. So any other questions? We'll go to next. So I will just discuss quickly a protocol, a quantum communication protocol. I hope either Riktim or Nilesh, anyone might have discussed this, but I will just revise. So two parties, Alice and Bob, they want to communicate in a way, they want to share some qubits. So what they will do, I can use sorry. So two parties, Alice and Bob. So they want to connect with each other. What's their goal? To share some secret qubits. So they will be connecting with two channels, first of all, quantum channel and classical channel. So I will be discussing general and then I will come to BB84. So classical quantum channel will be they will be sharing qubits. Okay. And classical channel, normal classical information. So in BB84 protocol, what they do, they have a laser source and they are sending a single photons from their laser source, and they are using something called basis. So you know computational basis or cross basis. So like say horizontal, vertical, and this is one set basis set, and then this is something called diagonal, anti-diagonal. This is one basis, and then left circular, right circular. This is another basis. So these are nothing but polarization of a photon. So horizontal polarization, vertical polarization, diagonal, anti-diagonal, left circular, right circular. This is a polarization of photons. They are using this basis, and Bob is using for a measurement. You can keep it here. And Bob is using it for a measurement of those qubits. So he is also using either this basis or this basis or this basis, and it is totally random when to use what basis, which is totally random. So they have used, they have sent some, for example, 0 1 1 0 0 1 1. So this is the key, and they Alice want to share to the Bob. So whenever this, they will send some photon, and they will use some basis like H. They will use V or H or V or something DA or whatever basis he will use, and Bob will use randomly. He will just toss a coin, and whatever outcome randomly he will going to use. Let's say vertical, diagonal, anti-diagonal, horizontal and vertical, horizontal, diagonal, anti-diagonal, left circular, right circular. So most of the time their basis will not match. So classically they will share their basis, not their key, but their basis they will share between both the parties, and they will match their basis. In which case their basis is matching, they will just keep those values, and rest where basis will not matching, they will discard. So first process, sharing the key by using a basis through a laser light single photon source, and here there is a detector, and the other guy is measuring it by using his basis. Both bases are random, but after sharing, Alice is sharing the what basis they are using, and public channel. And let's see, there is a eavesdropper in between. If there will be eavesdropper who, let's say Charlie or something, Eve in between. So if Eve wants to know what is sent by Alice, then she will also going to use a random basis measurement, and once she will use that random basis measurement, the number of mismatches will be huge, because Alice in between, and because of the no cloning theorem, she is disturbing the data. So there will be threshold number. If the mismatch or error rate is coming beyond that particular threshold, then both will discard the operation, and they will know there is some mole in between and somebody is listening our communication. So they will discard it. And if it will comes beyond the certain threshold, then the communication will be happening perfectly. And this is the way one of the so what will be the rate, how you will calculate the bit error rate. So this number of mismatch bits, so this is the formula of Kuber, number of mismatch bits divided by total bits shifted key. So that's how you calculate Kuber if communication is happening. So this was the protocol. I have explained what is the security, eavesdropping detection. So there will be, if somebody is hacking the data, you will know. And unconditional security, in principle, these quantum communication protocols are very secure in nature. And error rate calculations, as I discussed. So this is a protocol called prepare and measure. So there are no entanglement in between, you might have noticed. So prepare and measure, where no entanglement is involved, and there is one more protocol, setup protocols, which are called entanglement based protocol, so where you are going to use entanglement, and security of entanglement based protocol is next level. Here, if you're using some quantum computer or some attacks, quantum attacks, you can get some data. But if you're using entanglement, other types of protocol, you are absolutely secure and nobody is going to break the system. So this is one protocol. I will have. Thank you. Meanwhile, if you have any doubts in this protocol, please ask. Anyone have any doubts? So I will come next to our most important part, which is called quantum repeater. I have already given some glimpse in yesterday's session. Now I will discuss deep what is the whole entanglement swapping and quantum repeater protocol. So you remember this entanglement generation we did yesterday by using a non-linear crystal. We pumped it, we get signal and idler photons which were entangled. So assume that you all are a node. Every one of you are node of quantum, you all have some quantum source, detectors and trans receivers, everyone you have. Now if sir wants to connect with you, both professors wants to connect with each other, so how you will do? So first, and assume that who are sitting next to each other, they are directly connected, right? So this is a network we have here. Now these two are directly connected, these two are directly connected, these two are directly connected, and so on and so forth. Now let's say if sir wants to connect to other sir, so they have to first know which way is coming in between, what is the direct path, so which is called a routing in a particular network. So first you will do a quantum routing, you will analyze the resources of multiple path. Let's say you have an n number of path, you will find out which path is lesser in time and lesser resource exhaustive. So you find a path, let's say this is the path. Between you and you, there is 4 nodes are involved. Now what you will do? First, directly connected nodes will create entanglement with each other because directly they are connected. So directly connected, and how many entanglement? So you have to, so there is something called fidelity which Diksha discussed. So fidelity is the quality of entanglement. If let's say I am telling out of 100, if your quality of entanglement, which is called fidelity, is below 70, you cannot conduct certain quantum communication protocol. So 70 is a required fidelity, 70%. Out of 1, 0.7 is required fidelity. But you have generated some entanglement which has fidelity is 60%. So how you will do? You have to do something called purification. So purification of entanglement, so where you can use 2 entanglements between A and B, there is 2 entanglement of 60% fidelity, 60% fidelity, and you do certain operation, and this 2 entanglement become a single entanglement and fidelity increased. it's 70% fidelity now, but two entanglement converted to single, two pairs converted to one pair, and fidelity increased. So this is called entanglement purification. I'm not going to give the mathematics of it, it will be too long, but this is called purification. So if required fidelity is more and achieved fidelity of entanglement generation is less, you have to start with multiple number of pairs and you have to do purification in multiple times to get to achieve a required fidelity. So purification is clear. So first you will generate entanglement and number of entanglement will be high. To achieve the required fidelity, you mix multiple entanglement and create a high fidelity entanglement. And then what you will do? Once achieved 0.7 and 0.7, let's say A, B, C, D. So 0.7, 0.7, 0.7, this fidelity has been achieved. Then you do entanglement swapping.
The qubits will be reduced.
Means quality of entanglement will be increased, but you have to start with more number of pairs. Yeah.
Only looking at the diagram, I thought the number of qubits will be reduced.
So you will start with, let's say, all these qubits has fidelity 0.5, 0.5, 0.5, and these two convert into one, these two convert into one, and now you got 0.7, 0.7 fidelity, and you did a swapping between them, right? So these four pairs became into two because the swapping done. Same phenomena is happening to other as well. So entanglement generation, purification, and swapping. So now swap, now you see two pairs here, two pairs here, and after swapping as well, fidelity may go down. So you do again purification. After swapping, you do again purification, and then these two become one and high fidelity. These two become one with high fidelity, and then you do a direct swapping. So let's say sir want to connect with another professor. So you have to start with 10 entanglement pairs and you sacrifice entanglement pairs in between, and now you are connected with a very good fidelity. Now you can do distributed quantum computing between this and this. You can do a teleportation between A and D. You can do a distributed quantum computing. Either you can teleport your quantum information, or you can convert, you can send your even non-local operation. So I was discussing previously a non-local CNOT gate. So a non-local CNOT gate can only be developed if you have entanglement between two non-local nodes. So is this clear? Any question in this? Okay. So that is, I also discussed the part of quantum internet protocol. So this will be a future quantum internet protocol as well. That's how it will work. So why we are doing this? Because directly if we will sending this to this, there will be a loss which increase exponentially with length. So exponential 2 alpha L. So this is the power law loss information. So I'll go to the next. So how the whole quantum network or internet will evolve? So steps will be like this: point-to-point QKD as Alice and Bob. There will be something called point-to-point QKD. Then trusted repeater. What previous slide we discussed was repeater. So trusted repeater, and then entanglement distribution network. If you connect a whole number of quantum devices in a network, that will be called a quantum distribution network, and at the end you will get stage 4, which is a full quantum internet. So what are the essential devices that are required? So my focus is mostly on quantum hardware side. So we work to develop those devices which will be the building blocks of that startup network. So what are the major parts? Quantum memory, quantum transducer, and high fidelity entanglement source. These three are the backbone of what we have discussed so far. So as we have to start with a very high fidelity entanglement. Step 1, we should start with a high fidelity entanglement. And quantum transducer, as sir's question, what is the difference between data qubit and communication qubit? So there will be a transducer. Let's say, for example, a superconducting qubit is connected with a photonic qubit. So there must be something called microwave, low temperature microwave cavity. So which connects the superconducting qubit, which we deal with superconducting environment with a microwave. So microwave to optical transduction, that will also happening inside a low temperature refrigerator, which is called dilution refrigerator, and that is something called quantum transducer. So this is one example of quantum transducer. There are n types of all permutation and combination you can check. So there will be multiple types of transducers that are required for a distributed quantum computing. And quantum memories, of course. So in the previous slide you saw these are the blue dots. What are those? All are those quantum memories. So if you don't have very high coherence time or storage time quantum memory, how even you will hold the quantum information? So you created entanglement photons, but to hold them, you should have a quantum memory which can hold the photons for, so for example, you started from here. So this photon should be alive till all this process will be completed. So let's say this process is taking 1 nanosecond, and this is around microsecond, this is around millisecond, this is around second. So at least 1 second this quantum storage or this should have second level coherence time. That much time it should store, a quantum memory should store. But our quantum memory state of the art is what? In microseconds or in milliseconds. So what is required? We should have quantum memory with storage time high. So high coherence time or high storage time quantum memory are very essential, along with the transduction and high fidelity EPS. Okay. So and at the same time, as I discussed previously, this is the niche era of quantum computation, and error correction is must. So there are not very fault tolerant quantum computers, so we have to do error corrections as well to ensure that whatever operations we are conducting, that is very less noisy. So error correction is very much required. So now we'll discuss something, we'll deep dive more into distributed quantum computing. So these two terms, one is called teledata and telegate. So these are the two important terms. If you will go very detail into distributed quantum computing, you will see teledata and telegate. So we know the teleportation we discussed in previous session, where you can teleport a quantum state of a qubit, not the qubit itself, not the physical particle itself, but the quantum state which it retain, you can teleport to another qubit which is not directly attached with that. So here you see what has been teleported? Quantum data. So quantum data has been teleported. So where the quantum data has been teleported, it's called a teledata. And there is another case where a quantum operation itself get teleported. So that is called a telegate. So for example, you have sent a Bell state or example single qubit quantum information, horizontal and vertical का superposition. So ket h plus ket v by root 2. This is a quantum information. You have teleported by using a teleportation circuit or teleportation experimental setup. You teleported that. Then this will be called a teledata. But what if you teleported a C0 gate itself, or Z gate, or any Toffoli gate, or any sort of control swap gate? You teleported the gate itself. So that comes into the category of telegate strategy. So they have different concept, advantage, cost. So you can just check it. So each have their pros and cons, and contextual. They are very contextual, in which context you have to use your telegate, and in which you have to use your teledata. So I hope this part is very clear. Any question? Which one? Telegate, yes. I'll show one example where distributed quantum computing, not very long distance but very shorter distance, it's been done. Hardware. So there is a paper of Nature in 2024. You can take a picture of it and you can check. So that is that. So when you will use each strategy, so where data is required to be sent, you will telegate teledata. Topology has to be dynamic, routing capabilities, and intermediate measurements are part of the protocol. In telegate is where like operation stays local, and the whole gate is being transferred. So that's the difference between two protocols. So now we will again check the teleportation, the telegate. So telegate can be done like by using teleportation, where first you should start with entanglement pair, and Alice does a Bell state measurement at its node, and then classical information that comes after that, which was shared with Bob, and Bob reconstruct the initial information that we have. So that's the solution for telegate, which is quantum teleportation, nothing but quantum teleportation. We have discussed multiple times. So this is the, I think, repeating slide. Yeah, and if you want to do a telegate, then you have to do a entanglement swapping or virtual links. So we discussed the virtual links before. So once you will conduct, so assume that you have data qubit, you have transducers, and by using transducers you can connect directly with another processor, or you can do a virtual links, which is nothing but entanglement swapping. So by using this kind of strategy, when two non-connected or non-local processors are connected by a virtual link, so where you can do a telegate operations as well. You can directly transfer C0, or so C0 is what? Control is on a different processor, and so other part, the swap, is in different processor. So these two are non-local processors. So this is something, one example of entanglement swapping between multiprocessor. And again, the Bell state measurement, the conditional operation, and this virtual nodes and direct nodes, those will be the important part of it. So what are the benefits of this entanglement swapping or telegate? So it's reduce physical connectivity, enable arbitrary topology. Topology is, the network topology is very simple, a mesh, or circular ring topology, or whatever linear topology. It depends on the topology of the network that you can have. So it enable all sort of topologies, and there are very scalable, that swapping part, provided you have the elementary requirements met, then it will be very scalable. And the cost and trade-off, so resource consumption, highly resource are required, like as you see, entanglement purification is highly resource exhaustive. You should have a multiple entanglement at start only. So if you want to go for 0.7 or 0.8 or 0.9 fidelity, you should start with 10 or hundreds of entanglement beforehand. So that's the resource exhaustion. And again, the complex coordination, you have to have a scheduler, you have to have a complete central controller which controls all the operations dynamically. So these things are requirements, they are a must. So modular gate teleportation, how you can do? So first you have to establish the network, the circuit qubit, auxiliary qubits, and by using all of them you can conduct a very distributed quantum telegate by using the entanglement swapping. So main part is photonic interconnects, that in form of transducers, how superconducting qubits and photonic qubits, they will talk to each other. So that will be major interconnect, and our quantum memory and our EPS, those are designed that way so that it can work at room temperature and act as a photonic interconnect. So now one more telegate application where non-local gate can be implemented. So what are the types of telegate implementation? So first is 2-qubit entanglement can be used, like C0 or something. So that is called gate decomposition, teleportation based. And another is a cat entanglement method where GHZ. So GHZ means 3-qubit entanglement where 3 parties are entangled with together. So that's the cat entanglement method. And hybrid method, either you can use teledata or telegate or both in a hybrid fashion. So that is the hybrid strategy that can. So I'm not going through the detailed mathematics because at very initial level this is not required. So if you're interested much, you can go to the reference section and check the mathematics of it. So deliberately I'm not giving the maths, I'm just giving some ideas. So C0, what you will do, let's say if you want to do a C0 non-local C0, then first EPR pair and C0 to EPR half and measure S and send, and then conditional corrections. So multiple steps that will involve. What you will do in those steps, you will optimize objective like minimize EPR consumption, how many entanglement to start with, you have to minimize, and circuit depth you can reduce, and balance the communication and computation, mitigate the error propagation. So these things should be optimized in that process. So key hardware, already we discussed few of them like processors, memories, transducers, and photonic emitters and detectors. These are also important factor, because how efficient you are going to detect, then your process will be more efficient. So these detectors are also important. And fidelity requirement, each section, what is the fidelity is degrading at each sector or each step, that is also very important. You have to have very high fidelity if you want to do a useful operations. And performance matrices will be gate error rate, memory coherence time, entanglement generation rate, and quantum bit error rate, which is a QBER. I have discussed this QBER in previous example of BB84. So where total mismatch, so mismatched qubit divided by total qubit, shifted bits. So ma'am, I will come to your question. So you ask if something has done or experimentally achieved or not. So yes, it's been done. So this paper in Nature 2024, so first deterministic distributed quantum computing has been done. What are the achievements? 99.7% fidelity has been achieved. So gate teleportation, C0 has been teleported. So we are asking that. So gate, which gate has been teleported? Which is C0 like operation. And they have a coherence time, their type of qubit is 1.2 second, which we were discussing, second level coherence time will help. And what are the distance is 1 kilometer. Within 1 kilometer it's been set. So experimental setup, what type of qubit it was? A trapped ion architecture. So trapped ion quantum computer, where a distributed quantum computing, a photonic interconnect was used. So trapped ion, what was the transducer has been used? From trapped ion to a photonic qubit. So these were the transducers has been used, and these are the results. And gate error rate achieved like that was less than 0.1 for local gate. Memory coherence exceed more than 1 second. Entanglement generation deterministic within 100 per second. Photonic link efficiency around 70. So you can check the paper, you can find all the detail. I just kept few detail which were prominent. And what are the significance? Means DQC is not just some kind of theoretical idea. After the experimental proof, this is something can be done. So, and if we have all the interconnects or key ingredients are more practical in nature, very high coherence quantum memory, very highly efficient transducers and sources and detectors as well, then we can find out we can realize a very long distance quantum network or distributed quantum computing. So we are coming to the end. So mostly it's been discussed the overview. I kept it very non-mathematical in nature, but you can go very deep into it, and all the mathematical information already there in the reference. So why distributed quantum computing matters beyond academia? So cryptography and security, drug discovery, material science, financial services, optimizing portfolios or financial institutions optimization, AI or machine learning, this can be used, logistics and optimization as well. So these are the applications of it, distributed quantum computing, which is a very promising area of coming quantum technology. So that's all from my side. These are the references. You can click a photo of it, or you can get a PPT later, and you can check the references for the whole detailed mathematics part of it. So that's all from our side, and by ending this, we are ending this session from Quantum AI Global. So if you have any more questions, you can ask, or else we'll be commencing. Any questions?
Yeah.
Okay. Thank you. Thank you so much.
You are to that session of the fundamentals of quantum computing. Let me invite Professor Giri Mohan, and the Dean School of CST IIT is also the partner of this. I would like to invite Mr. C. Gururao sir to show his CSC. Lots of coordinate of this activity. I would like to invite Dr. Devendra Mishra, Quantum Hardware Lead Quantum Air Global. Before calling upon the coordinator to know the advanced to call upon the participants to give
Not online feedback. Live feedback here.
Please.
How did that? Renu sir from here. Madam. One from electrical department. Jagger sir.
First of all, I thank the organizers for giving this opportunity to participate in such a nice workshop. So all the speakers from Quantum AI Global are very informative and explained very well from the start onwards. Especially even the lecture. Like BTech first year students, how we are injecting slowly and like that we can inject and come out. It's encouraging. So, thank you, one and all.
so much, sir.
Good afternoon, everybody. It is a wonderful journey. Quantum AI global people, organizers, Gururao sir, Madam, Pushpa sir, they arranged an excellent training program and creating technology frontier area introduction. Quantum AI appears to be a small company, but they are turning it into a pioneer. Whoever visited and whoever given lectures, they are well versed in the subject, they are highly knowledgeable, and they are able to transfer their ideas and knowledge into participants like us. Very good. Hope your small effort will contribute to institutional growth, institutional operation. Whoever visited our campus and given lectures, thank you one and all, and I wish you all the best. Success in your future, Quantum Global AI engineers. Thank you.
From the sales department. So we completed our undergrad for quantum computing, but we want to take a full miss from Quantum AI Global. So actually, all the 5 days, we were able to understand and we tried, and but the energies of all the speakers, especially the smiles of Ankit and Diksha. So they, with all the energy and smiles, so you turned our sleepy mood and grabbed to listen all the lectures. And one request from our side, as we belong to EC department, so we more like to focus on the hardware. So with the help of organizers, so we request you give an opportunity to visit hardware, especially if possible, so that we and our students will try to learn and bring new science with all your help. So it was very nice. Thank you, madam and sir, for this opportunity. Thank you.
Good evening, madam. My equity madam asked me whether are you interested to participate in a on quantum computing. Then I feel that it may be very difficult to understand. Now I feel that I can start and work on it. So that's my feedback. So it means many topics are clear. So I have many doubts, but now I can start on this particular topic, quantum computing, which plays quite a role in future communications. So thank you very much, CSE department and I'm Dr. Srinu Paila, Associate Professor of TCE, GP College of Engineering, Kadapa.
I request outside faculty come see them. Okay. Okay. Sir, online. Yes. Nobody is responding, sir. There are actually 10 participants.
Now I request Professor K.P. Malik.
Cutting our opinion.
Respected academic department. This resource person. Devendra Singh. Professor Professor. And all the rest of the departments. And my dear faculty. Good evening to Vanita. First of all, from my bottom of my heart, I thank all the resource persons, starting from Subbarayareddy garu, Dr. Subbarayareddy garu, and external Kavindeshwar garu, and other resource persons, Gupta, Ms. Nisha Sharma, and Kadya,
and his team and the Devil's team. I thank all the resource persons for taking keen interest in organizing or taking the lectures. Actually, all the lectures are very interesting and informative. We are new to this area. So now we got some idea. I won't say we are big experts. I cannot say even I don't have that. So, but we got some idea. Now we got confident that yes, we can introduce my and even in future also, just now this in our session we have discussed why don't we start BTech quantum computing. So we'll see. And please convey our regards on behalf of the GVP College of Engineering. Please convey our regards and special thanks to Mr. Sanjay for taking keen interest in sending the resource persons and to educate our faculty. And special thanks to Ms. Gopika, who is the SWAT from Quantum AI Global, and thanks to Dr. Anuradha Madam. She's the SPOC from our college. Actually, she's the amazing secretary. So, Madam, thank you very much, Madam. I think she's not but all the lectures are very interesting and informative. Even in future, we are planning to organize many more MTP programs, student training programs, hackathons, and so on with Quantum AI Global. And even we would like to invite as a special invited to our board of studies by designing the syllabus. And in this semester, that is next semester, even semester, we would like to introduce minor program in quantum computing. So for that, we need your help. Please pass on this message to Mr. Sunday. Even we have discussed with Mr. Sunday. Start this with one of my professor, not tell the name, but he was gone into multiple other field and he was new to quantum. He told me in a cycle for moving a bicycle is very easy, but moving a 16-tire truck, trailer, taking a turn is difficult. So we are students, we are like a bicycle. We can turn very quickly. Let's say we are studying condensed. We can very quickly jump into quantum computing, quantum optics, or anyway. But being a professor and having a long time in your field, saturated with teaching and all area in your field, but daring to get a new technology, learning it, and try to teaching it, it's as difficult as moving a 20 cars or 16 cars vehicle. So it's daring you are doing, and thank you so much for that. Okay, so it's been pleasure, and on behalf of my CEO, CTO, and whole company, I'd like to thank you all for giving us opportunity to deliver what things we are doing in shallows, give it back. Because we are also from some academic institutes, and professors like you taught us. That's why we are here. So it's a form of give it away. So we are very happy and very glad
that we can do because you have given this opportunity. So thank you so much, and thanks again from behalf of my team QIG, and I wish we'll come next again very soon, and we'll come with our hardware. Our new people I'm inviting who wants to come to our lab, so we are very open to discuss with academic people, so you can come to our lab and we are more than happy to show you what in person, what we do, what kind of technologies we are working on, and how it is useful for the community. Thank you so much.
Sir, now it's really doing ourselves.
Good evening, everybody. Tina. This evening, yes. Last but not least, because then start and counterparts the professors, heads of departments, and the participants who have been directly attending this program from all the families. It gives me really an immense pleasure to go ahead with the quantum global AI. MOU. Same day, I propose this every and another 2 months preparing paper has given this particular thing. In fact, they were talking about 40-hour programs. Somehow we are able to get them accepted for 5 days. It is also a very big really effort made by them. All of the lectures starting from their CPO to last doctor, Devinder, have been wonderful. Of course, Professor Subbareddy has laid down the foundation of basics on the entire, of course, not actually, but whatever is the basics required, he has given us. Actually, as a teacher, I really love all to see here because you have one foot forward to learn more, and particularly new technologies. As we said, turning a 60s bad vehicle. Obviously it is not that good, but we have made it. And I request all of you to please try to take some time and try to engage more in giving some projects, doing some kind of work. Now that a lot of resources have been exposed, so you can always take these leads and try within your. The wonderful thing this workshop has is that it has brought all the departments together, and I feel more of multidisciplinary or interdisciplinary projects will come up. That's what is required. And I take this opportunity. I have one offer. I put it in the book. Like I have one book series there, limited book series is being granted to me. It is posted on the website. The details I put where you can use smart applications of healthcare devices. If anybody is there, you can really take it and make it successful. At least writing by submitting one check. Not only that, we can always look forward to for more activities like this, maybe in the near future, turn out with the help of quantum global AI in different specific fields. Now we can, because we have taken the fundamentals, we can go specifically into one of these fields. And a quantum global AI then MOU with the institution. So all the departments can wait, not a problem. We can really go. And I expect that you will also enable some students by delivering the relevant content, maybe quantum communication and networks for VC and other materials and other things. All those four or five things are there you can take up. And I think you will come up with a lot of such kind of MDB proposals to us so that all of us put together, that is why I said we are involving everybody. That is what has been the plan. I thank all the speakers, including the CDO, Kapil Jaswal, and and Mr. Sanjay Chituri, who has been unconditionally accepted and spared his entire resource with us. This is a very great gesture. It's a gesture he has made to Gayatri Jayaprasad and Department of CSC and all other allied departments. In fact, every department must be indebted to, because the other day I just passed on to CSC faculty members. I received one email to really enroll into similar kind of program and rate 15,000 per day. I just want to advise you that what must have been. It is in our campus they have delivered such a beautiful program. So I wish everyone very success for this. And I thank everybody, all the organizers, including all the faculty members of CSC, IT, MCA, CSC in sense I make CSC DS and CSC AI. And in fact, but in CSC, cyber security is also included here. Even though no faculty member is there, they try to switch up that thing. And all the non-teaching staff, including Sai, and I should thank, and the media people on the name here made a very rich effort in extending the YouTube as when the request came from, and we have displayed, we have broadcasted it to a group of 2-3 groups, very which few people have joined in that YouTube live and made it happen. I request all the participants also, please look at by morning we shall deliver the email containing all the instructions of the test. And you will be given time, you will have sufficient time to go through and attend those 20 questions only and think yourself. Even otherwise, if somebody is not picking up, we promise you to be a participation factor. Nothing wrong with it, right? I thank all of you very much. Thank you.
Thank you so much, sir. Now let me take the immense pleasure in conveying vote of thanks on successful completion of this event. Now I call upon Professor C. Gururao sir, Professor P. Madhu madam, Professor Srinivas Putla, Professor Jagannathan sir. Professor P. Umadevi madam. Esteemed speaker. Small thing. Your etiquette depends whether you can vote of thanks on successful completion of this activity. Over the course of this activity, we have been fortunate to learn from eminent speakers who generously share their time, knowledge, and expertise with us. Quantum Dr. P. Venkateswara, Professor NIT Warangal, for clear explanations, statements, and structured approach laying a strong foundation on the basis of quantum computing. I would like to thank Mr. Sanjay Chituri, CEO Quantum AI Global, Mr. Kapil Jaishwal, CEO Quantum AI Global, and the entire team of Quantum AI Global for well-structured sessions, clear explanations, and patience guided through which they took us from the very basics to the more advanced topics, ensuring that no one was left behind. The way the speakers combined theory with practical insights has enhanced our knowledge, understanding, and also motivated us to take these learnings forward into our classrooms and research endeavors. The way they conducted hands-on demonstrations and real-world case studies is truly admired. We sincerely hope to stay connected and continue this journey of learning and collaboration in the future as well. I'd like to thank the management of GBP for their unwavering support and vision. I'd like to thank our principal, Sir Professor Alpoteshwar, sir, for fostering this initiative and providing seamless administrative coordination throughout the activity. I'd like to thank the coordinators of this activity, Professor C. Durrao, Sir, Professor K.V. Mountain, Madam. Their unwavering support and motivation during this activity and coordination, every detail reflects a true commitment and was extremely admired. I would also like to thank the organizing committee members, organizing secretary for their constant support and sincere efforts in making this activity possible. I would like to extend a sincere thanks to the management and principals of all other institutes of GBD for their support. I would also like to thank all the deans, heads of various departments, faculty, technical and non-technical staff for their continuous support. And as Ms. Bobka Charity has mentioned, I would also like to all the lovely participants from various departments of various UP institutions for their active participation. Your enthusiasm, insightful questions, and collaborative spirit turn this activity into a vibrant learning community. Thank you for your active engagement. Finally, I would like to thank Ms. Deeksha Sharma and Mr. Aniket Kalia for acting as these masters. Thank you. I request all the speakers to come forward and participate from our group.